welcome to the lecture on programming, data analysis, and deep learning in Python. Today we're actually talking about data analysis, which I think it's a quite exciting topic, and it's also a topic that that you will probably spend quite a lot of time on. And the tool that that I'm introducing today is Pandas. It's a Pandas library. It's described in this book, Python for Data Analysis. So if you want to do some data analysis, this book has a nice introduction. It has a short introduction to Python. Then it has a short introduction to NumPy. And then it has a lot of pages about Pandas. So if you want to have more details about Pandas, and how to do data analysis, I would recommend this book. So when you graduate from university and you start working in some company, I'd like to ask you to do one thing, and that is to walk around your new company and to find some person who's working with Excel. And I can guarantee you, you will find some persons working with Excel. And then I ask you to ask these people what they're doing and for how long they have been doing it. And I think in almost any company, you will find some person who will tell you, oh, I'm preparing these and those reports, and I'm doing this and these analysis, and I've been doing that for 20 or 30 years, every day, 8 hours. And then you should spend a few hours having them explain you how they do it. And then I ask you to write a small Python program in Pandas that can do it. And so that the entire job of that person will be completely automated. And then you can show them the program and tell them, oh, what you've been doing for the last 30 years of your life, actually, my script can do it. I think that will be, and then take a video of their reaction and send it to us so I can use it in the lecture. Okay, it's really surprising if you go out there, if you go into companies, how many people do the same stuff in Excel over and over again, and that makes absolutely no sense, right? I mean, if you do it 5 times, it's okay, but if you do it 10 times, it's already less effort to write a program to do it, right? And then you can schedule the program to run every night and do it, and there's absolutely no need for a person to do it. Okay, so. If you're working with data, who of you has worked with real-world data, like measurements or some data from somewhere? Okay. Who of those who have worked with data found that the data was chaotic? So it was not like super clean, it was unstructured, it had missing values. Okay. Did you work with real data, or did you work with fake data that somebody provided to you? Real data? Real clean data. Okay, that's very rare. I can almost not believe it. So if you go out there and you work with real data is almost always chaotic. Real data has missing values. It has like different labels for the same thing and the same label for different things. And it comes in strange formats where stuff is distributed over multiple files, and some stuff is in text, some other stuff is in some strange formats, and so on. And if you want to analyze the data, probably in the end you want to put it into like a NumPy array, an ND array. But the way from real data to your NumPy ND array, that's a very long way, right? That's very difficult, and that's what Pandas is actually good for. So Pandas, it's short for Python for Data Analysis, but I think that probably most data analysts spend like 90% of their time not with data analysis, but with data cleaning, right? So it's Python for data cleaning, and after you're done with the cleaning, data analysis. Okay, so it builds on NumPy. And the main difference between, what the most important thing that Pandas does for you is that it introduces 2 new data structures beyond these tensors that you get from NumPy. So from NumPy, you get vectors. You get this n-dimensional arrays. So it can be 1-dimensional vector, or it can be a two-dimensional matrix, or it can be a three-dimensional or any dimensional tensor. And what's implicitly assumed in NumPy, or can anybody say what we assume about the data in these, in the ND arrays? So if if you have an ND array, can you assume something, or does this data in that array have to fulfill some like conditions? Yes? Yeah, it has to be a number. It doesn't really have to be a number. It can be different data types. It can also be Boolean. But the main point is that all these entries have to be the same data type, right? And that's the biggest constraint for a lot of stuff that you're doing. So all same data type. Whereas if you go in the real world, if you go out in the real world and you get some, who has ever worked with comma-separated value files? Something .csv? Okay. If you go out there, most of the data is in CSV files, I would say, or in databases, or in some strange format that you have to parse. And most of the data that you find is actually slightly different from, so it doesn't have all the same data types. So most of the data that you have comes in something like an Excel sheet. So you have columns and you have rows, and most of the time all the columns have the same data type. So all the entries in one column are of the same data type, but different columns can be different data types. So this can be a float, this can be an integer, this can be a string, right? So this, what we assume here is that columns have same data type, but so within each column, so within each column there's the same data type, but the different columns can have different data types. And then there's also something else, and this is that often the columns and the rows have names, right? So you have here, this is name 1, or this is called, I don't know. This is called, I don't know, size, weight, name. And maybe these are different students and they are indexed by, I don't know what, maybe matriculation number. So this is 32142 and so on. So the main differences are, one, that different columns can have different data types. First difference. Second difference, that the columns have names and the rows have names. Whereas in a NumPy ND array, all the entries have the same data type. You cannot give names to the columns and you cannot give names to the rows. So you can only refer, in an ND array, you can only refer to it by index and not by name to the rows and columns. And if you get one of these columns, so the origin is from the Pandas library, is that it comes from a quantitative finance firm. So it comes from Wall Street. So there's been one guy working in some quantitative stock trading company. And of course, he started with time series. Who of you has worked with time series? Okay. So in time series, you have time on the x-axis. And you have something on the y-axis. And for every point in time, you have some value. So this can, for example, be the stock price of something, and this can be, I don't know, the seconds, so this can be, so this is sometimes some date plus some time on that date, so it's often off to date time. So it's the 1st of November of 2019, 3 p.m. and 20 minutes and 45 seconds and 200 milliseconds or something. So this could be an entry here. And this is actually a special case of one column here, where the row labels are actually the time instances. So what kind of time series have you been working with?
Temperature.
Temperature. And what was the sampling interval?
I think it was days.
Okay, one sample per day. Okay, so this can be sampled on very different scales, right? It can be one value per year, or it can be one value per day, or it can be one value once in a time. It doesn't have to be equidistantly sampled. But it's very convenient if the distance is always the same. Or it can be once per millisecond or once per nanosecond, depending on, I don't know. I guess if you work in physics, you sometimes can have very short time intervals here. Or very long time, and maybe this is 1,000,000 years from one step to the next if you do, I don't know, some astrophysics or so. Or geology. I think if you work in geology, then you have very long time intervals here. And there can be some very inconvenient things in this data. So one is missing data. So there's a time here where you don't have any data. So you don't know what. Did you have any missing data in your temperature readings?
I think so, yeah.
Yeah. So that's quite inconvenient for a lot of math if there's some missing data in there. And Pandas is really optimized for dealing with missing data. So your program doesn't crash, but it deals nicely with missing data. And one other inconvenient thing is maybe you have one measurement of temperature and then you have another measurement of humidity, maybe, and they come from different devices, so they're not sampled on the same, at the same sampling rate. That's very inconvenient. And Pandas has some support to deal with that. Because if you want to put a time series into an ND array, what's a big problem if you put a time series into the ND array and then you start to do some calculations? You could just say, oh, this is just a very long vector of all these values, and that's it. Yes?
There would be like no representation for the time.
Yes. You lose the entire representation of time, right? So you can put all the values into the ND array, but you would lose the index. So afterwards, it would be very difficult to reconstruct which point comes from which time. And if you have, for example, you have one measurement of temperature and one measurement of humidity, and they are differently indexed, then it's a mess to do it with ND arrays, right? Because you lose all the connection of the values to the index. So I think the most important thing to understand about Pandas is that you always have an index. So you always have an index here for the rows and for the columns. And as you keep calculating, the connection between the values and the index is always preserved. So you always maintain the connection between the values and the row and the column index. Okay. So I think that's probably enough explanation. Oh, who has done some data analysis in Excel? Oh, okay. Who thought afterwards that that was a good idea? Okay. Did anybody find a problem with Excel?
Well, firstly, it's kind of limited to a certain amount of observations.
Yes.
Like 200,000 something.
Yeah, I think Excel can do 1 million observations, but if you have more than 1 million observations, Excel just crashes. So, and I think if you work with, I don't know, if you work with small data sets, that's okay. But with any kind of serious data set, that's a joke, right? 1 million observations is nothing for a lot of like serious data sets. Yeah. You had the same problem?
No, the problem inputting calculations or formulas for your calculations is extremely annoying in Excel.
What's the annoying thing about writing your program? So there's actually, if you go out there, if you go into companies, you would be surprised how many programs are there that are implemented in Excel. numerical programs, in a way. What's the annoying thing about writing programs in Excel?
Well, first of all, it's in German, because if you have German Excel installed.
Okay, so all the function names change. Yeah, that's great. You have a programming language where all the function names change depending on what language you're using, right? You have German, French, English, maybe Chinese function names, yeah.
But there's a couple of things like it's very slow depending on the calculation.
Yeah, if you have big data sets, Excel can get very slow.
Even
Yeah.
so it's small.
Oh, even on small data sets, Excel can be slow. Okay, that's interesting.
And, also, like if you want to do some real programming, like the VBA, the Visual Basic, it's like one of the worst programming languages that there is. It crashes really often. It's not reliable.
Excel crashes. I think the biggest problem of Excel is the following. You get your Excel sheet. It looks like this. And if you write your program by putting formulas into the cells, right? Where is your code? The problem is you do not see the code. You only see the code when you click on the cells. So your code is basically hidden, right? The entire, I mean, unless you do some Visual Basic stuff. But if you enter a lot of formulas in the cells and the code is hidden, and if you have a very complex calculation, try to debug that. Or you get an Excel sheet from somebody else and you try to understand the calculations that they're doing, and all the code is hidden in some cells. That's a mess. There's a story of some analyst at McKinsey doing some important project, and they make some very important decision about building some factory somewhere, and then somebody asked, oh, why did we make that decision? And then they went back to look at the Excel sheet, and there was a bug in one of the cells, right? And so people make very important decisions with Excel that are very difficult to debug and very difficult to implement properly. Okay, so if you're having a toy problem, I'm completely fine if you're using Excel. But if you're using any kind of serious problem with like serious amount of data or important stuff or something that should be run very often, have a look at Pandas. So you have this library. It's called Pandas. Pandas is it's not very long, so we import Pandas. But we are too lazy to type, so we always say import Pandas as PD, just to make our life a bit less typing. I downloaded some data set from the internet, and I thought it would be interesting to look at the stock prices for Nokia. So on my hard drive, I have some data, and that's in this file. It's in my home directory, and downloads, Nokia, NOK, CSV. Okay, so this is just a string, and now if you want to open that CSV file, that's a single line of code. So in Pandas, we have two data structures. One is this Excel sheet style. This is what we call a data frame. And the other one is the time series style. This is what we call a series. But this CSV file, it's like an Excel sheet. So it's a data frame. So we create a new data frame, we call it df. So we say PD with CSV. And then we put in that string, data. And we say where the index for the columns is. Which columns should be the index. So the problem is, if you're opening a CSV file, there's a lot of columns like this. And we need one of the columns to be the index, to be the name of the rows. So you need to decide for any of these columns which should be the index. And I say that the index column should be the date. That's the most natural index, I think. Okay. So now Pandas loaded that file, And I think the amount of data that pandas can work with is basically limited by your RAM. So if you have like 200 gigabytes of RAM, then you can load pretty large sets of data. I have 16 gigabyte of RAM, but it's okay because the CSV file is very small. So the type of this thing that was created is a data frame. So that's the most important. So if you're working with real data, I recommend you to always first use pandas to wrangle the data into the shape that you need, and then afterwards you can use something else. But as a first step, I would always open the data with pandas. Then we can look at the first rows of that Nokia data with head. So head means the head of the table. So it looks like this. So on the left, the index is the date, and apparently we have one sample per day. So this is the 3rd of January 1994, 4th of January 1994. And then we have different columns, which is the open price of the Nokia stock at that day, so the first price that you get on that day, then the highest price on that day, the lowest price on that day, the closing price on that day, and then some adjusted closing price. Does anybody know what the adjusted closing price is of a stock? So I think the economists, they do some magical math to adjust the closing price for something like dividends and so on. And then there's a volume, like how many stocks have been traded on that day. And we already see the one interesting row here, this one. Here we have a lot of missing values. I think this is probably a weekend, and on a weekend we don't get any stock data because the stock exchange is closed. And pandas deals with missing values as not a number. So the code in pandas for missing data is a float. It's a float value of not a number. I think the creator of Pandas says it's not a great solution, but they will change it in the future, and apparently they never changed it. I think it's kind of okay. So if you use something like R, the R programming language, I think there you have something like that's called NA for not available. And it just means that either your sensor was broken or for some reason you didn't get any measurements for that sample, or it was a weekend so you couldn't determine the stock price. And you most of the time you have a lot of missing data in your data sets. Okay, but now we don't want to work with the full table. What I want to show you first is how to work with the time series. So as a time series, we can pick any of these columns. Does anybody have a preferred column? Maybe we just take the opening price. Let's just take the opening price for every day. And let's work with time series. Time series. Series data structure. And time series is something that you can also get from a sensor. Does anybody work in some field where you had some temperature measurements, right? Did anybody else work with some other time series? You can as soon, yeah.
Also work with inflation.
With?
Inflation.
Inflation, like the price inflation. Okay, yeah. Okay. Yeah, but it can also, if you work in biology, I don't know, maybe it can be population of some bacteria or something, or if you work in physics, it can probably be some pressure or whatever. Okay, so let's take the opening price as a time series. So we store it in a variable O, and if we want to pick an entire column, we can do that in the NumPy style. We just say, and here, this is already something that can be a bit confusing. So we treat our data frame similar to a NumPy array, but to index into it, we don't use the position, but we use the labels, right? So we use these labels up here. And if you just If you just put a single selection in here, then it's by columns. So with this, we pick this column open. Then we can look for the type. Type of O is, and here we see that it's a series data type now. Let's look at the head of that, O dot head. So this is a series. The data type is float, 64-bit float. Here you have the values, and here you have the index. And the index is date, and the name of the entire time series is open. It's the opening price. Okay, the first thing that I like to do with time series is plotting. And if we want to plot, we have to do one small thing here, I think. We have to say, if we want to plot not in a file, but we want to plot directly into this Jupyter notebook, then here we have to say matplotlib inline. So what this does, it tells the plotting library, which is matplotlib, to plot directly into the notebook. Okay, and then we can just say o.plot, and we get the plot. I think it cannot be much easier than that. And here we already see some interesting stuff. So we see this is 2000. So I think here we see the .com bubble and the Nokia prices, and then the .com bubble crashes, and then the iPhone. This is 2005. I think the iPhone appears somewhere around here. And maybe this is the post-iPhone crash of Nokia. And then the stock prices went down a bit. Okay, so in this time series, you can either look at it like this, or it's like a single column. Here we have the open price, and here we have the date. And for the individual dates, we get some price. And we can, if we want, we can get this data as a NumPy array. But if we do that, then we lose the connection to the index, right? So we can get the values, o.values. And it's an ND array with just all the values. And then you can do whatever NumPy stuff you want to do. You can also get the index with o.index. And this is the index. So it's of type date. No, the name is date. It's of type object. So I'm not sure what type it is actually. But it's all the names for the rows. And I think it's probably strings. And then we can look up the price for some date. And if we want to look, if we want to select something based on the index, then I recommend you to always use this o.log. It's for location, and then you give the label of the value that you want. Maybe let's look at 1990, or maybe we can. Oh, we have maybe 2018, 1st of December. Oh, it's not there. For some reason, it's not there. Does anybody see a problem? No. Maybe 2019, October 7. That should be there. Okay. So the stock price of Nokia, the opening price for the 7th of October 2019 is 4.9. euros, I guess. And now it seems that here's some interesting part where you had quite high stock prices. So for example, we want to detect where the stock price is more than 20. Then we can do this H for high stock prices. And this is where O is bigger than 20. So this created a new series. And you can also, so this series is of type binary, so it contains false, where the opening price was less than 20, and true, where it was bigger than 20. And you can already see that the connection from the index to the values is maintained throughout all the calculations. So you never lose the connection between the index and the values. And now we can say from this time series, you want to select all the values where this value in H is true. So from O, I want to have all the locations where H is true. And I can just do this. From O, I take all the locations where H is true. And I call this Q, maybe. And now I can do Q.plot. And now here I have only the dates where the stock price is bigger than 20. One thing that you will deal a lot with is missing data. For example, if we look into O, as our opening prices, we can check where there's missing data. And we just say O.isNull, just to ask where O is null. And this gives us like a binary time series. This is a bit long, so maybe it seems that it's always null where there's, so it's always four days where it's not null, and then there's 1 day where it is null. Oh, and then there's a missing day after that. So it's so 10, 11, 12, 13. We have values. Then we have one thing where we have a row, but it's not a number, and then we have 2 missing days. You can already see that there's a lot of issues that we might have to deal with. Okay, and maybe we want to calculate how many missing values we have here. So maybe we can say O is null sum. So O is null creates this binary time series, and with sum we sum up these values where false counts as 0 and true counts as 1. So this just says that we have 63 missing values in our time series. And then you can also, if you just want to check whether there's any missing value, you can say O is null any, and this tells you whether there's any missing value in that data. Maybe we are interested in the maximum and the minimum stock price of Nokia. We can just say O.max. So the maximum stock price was 61 euros, and the minimum stock price was €1.28. Oh, okay, that's quite a range in stock prices. Maybe we want to know at which date we should have bought Nokia stocks. So if you want to get the maximum revenue by buying and selling only once, maybe we want to see what date was the cheapest. And we already see that we could have bought Nokia stocks for €1.28. At which date? That would be very interesting. So index min. Index min gives us the index at the minimum. So we should have bought on the 1st of July in 1994. And then we should have sold index max on the 20th of June of 2000. Okay, then we would have made a lot of money. If we would have known that before, of course. And if we would have had a lot of money on the 1994, I'm not sure that everybody of you had a lot of money in 1994 to buy Nokia stocks. Then quite often we want the median, so O dot median. The median is 8.57. Does anybody know what the median is? Yeah. Yeah, it's some kind of average, but it's a special kind of average. So there's something that's the mean, O dot mean. So the mean is 13.06, but the median is 8.57. Yes?
So we take all the stock prices and we roll them up from highest to lowest.
Yeah.
And we just take the middle of these.
Yeah.
And then that's the median.
Okay, so the median is you take all the stock prices, you sort them, and then you take exactly the middle one. So it's the value where half of the values are smaller and the half of the values are bigger. And the mean, I think everybody knows the mean, is you just sum all of them, you just sum over all the stock prices, and then you divide by the number of things that you have. Okay, and if you want to, if you get some data, and then you want to get some overview of the data, one thing that you can do is to plot it, and the other one thing that you can do is just to say O.describe, and that gives you all the important summary statistics. So you just say O.describe, and then you see immediately that you have 6,400 values. The mean is 13, the standard deviation is 10.9, the minimum is 1.2. Does anybody know what this 25%, 50%, 75% means? Yes? Yeah. These are the quartiles. So if you have the minimum here, so you sort them from minimum to maximum, then the median is here. And this is also the 50% quantile. And then you have the 25% quantile and the 75% quantile. This is just how many values. So this is the value such that 1/4 of the value is smaller than that, and 3/4 of the values are bigger than that. And this is the 50% value, and this is the 75% value. And this gives you some indication about the distribution of the stock prices. And if you want to have a certain quantile that's a specific quantile, you can say O.quantile. And maybe you want the 50% quantile, and this is 8.57, which is exactly the same as the 50% quantile in describe, and it's also exactly the same as the median. Maybe you want multiple quantiles. Maybe you want the 25% quantile, the 50% quantile, and the 75% quantile. You can just give quantile a list. Okay, that was any questions so far about time series? Okay, that was a short overview of time series. Then we have data frames. When I data frame, I always think Excel sheet. Right? It's some kind of Excel sheet. It's not exactly an Excel sheet, but it's kind of an Excel sheet. So on GitHub, there's some data that I want to load, and it's stored here. So it's on GitHub. There's a iris.csv. It's a data set about flowers that somebody collected, I think 1800 something or so. So somebody went out and from these iris flowers, he measured, on flowers you have two kinds of leaves. You have these long leaves. Any biologists? Do we have any biologists in here? Okay, unfortunately, okay. So I don't know much about flowers, but somehow you have long leaves and you have short leaves on the flower. And one of them is called sepal and the other one is called petal. Anybody knows about that? And then somebody went out with a ruler and he measured the length of these and the width of these and the length of these and the width of these. And this is our data set. It's a very important data set in data science, because you can practice all kind of stuff on that. And I think they collected 150 flowers. Unfortunately, they didn't take photos of the flowers. I think back then we couldn't take, maybe they could have taken photos, 1890 or so. Yeah. But we don't have photos. Okay, so the data set is here under this link. So these pandas read CSV, we can just give it a URL. We can just give it location on the internet. And I hope we have some internet connection now. No, okay. So what pandas now did is went to the internet, it downloaded the CSV file, it opened it into a data frame. Or maybe I should call this df2. Or maybe I should call it iris, right? So we know which one it is. Because I think I already called this one df. Yeah. Okay, so we still have the Nokia one. Maybe it should be called Nokia. I will rename this Nokia. This one I will name iris. Okay. So iris.head. That's always the first thing that I do is I call head to have a look at this. Okay, so here we have sepal length. This is the length of the sepal leaves, I don't know, something, centimeters or probably centimeters. Sepal width, petal length, and petal width, and then this is the name of the flower. And then we could also say iris describe. This gives us a nice overview. So we have 150 flowers. The mean sepal length is 5.84. The standard deviation is 0.82. The minimum is 4.3. These are the quantiles, and the maximum sepal length is 7.9. Okay, this gives us already an overview of our data set. And I hope there's no missing data in this one. I'm pretty sure there's no missing data. And a data frame also has, like a NumPy ND array, the data frame has a shape. So we can say iris.shape. It's 150 rows and 5 columns. And they all look like this. Then we can get the columns, df.columns. And this gives us an index object, and the columns are open. Oh, that's df. I wanted to get the columns from iris. Sepal length, sepal width, petal length, petal width, and name. And if you want, you can throw away the column index and the row index and get the entire thing as an ND array. Does anybody see a problem with getting the entire table as an ND array? If we want to get this entire table here, this one, as a NumPy ND array, does anybody see a problem there? Yes?
Yeah, as we've already said, the last column is a string.
Yeah, the last column is strings, right? So we can try that. We can say so matrix A is iris values. Type of A is ND array. Can I say this? And the data type is object. So it doesn't help us much. We cannot do a lot of calculations because it's not numbers, right? But you can get the values as an ND array. And later we can see that we can select only these rows and get them, the values only from them, and then it will be a nice matrix with floats. Okay, so we get these values, and the shape is 150 by 5. And then we can index and do that with NumPy. So we take the rows 0 to 5. This is just NumPy and all the columns. And it looks like this. And the data type is object. Okay, let's go to back to our Iris data frame. We can get the index from this one. And the index, it's a range index. So it starts at 0, stops at 150, step is 1. And if you look here, so the column index are these 5 names, and the row index are just numbers from 0 to something. We can plot the entire data frame, iris.plot. And here we get the sepal length, the sepal width, the petal length, and the petal width. And we can already see that the first 50 flowers have a much smaller petal width and a petal length than the others. So there seems to be some structure in this data set. This is so semantically, this is a bit misleading because I plotted as lines, so I claim that I plotted as a time series, whereas the connections between these points don't make any sense, right? Because it's just individual flowers. So I should a bit more honest and not plot them as lines, but plot them with a different style. I just say style equals, or maybe this. This is a bit more honest. So these are our individual flowers. And I can also do a box plot. So I can say iris box plot. And I want to plot it by name, by the column name. And then it gives me all the possible box plots. So it gives me one box plot for petal length, one for petal width, one for sepal length, and one for sepal width, and the box plot are split by these 3 kinds of flowers which we have, which are Iris setosa, Iris versicolor, and Iris virginica. Yes. I can also do a histogram. I can say iris.hist, and then I can say how many bins I want. Maybe I want 20 bins. So here we have a histogram of petal length, of petal width, sepal length, and sepal width, with just all the flowers put together. I can also quite easily do a scatter plot. I just say iris plot scatter, and then on the x-axis I put sepal length. And on the y-axis, I put sepal width. Then I get the scatter plot, where I have the suspicion there's one kind of flowers up here in this cluster, and there's the other 2 kinds of flowers are down here. But it's not really easy to see from this because we didn't color it by name, right? Now there's a lot of different scatter plots I can do, right? I can put different things on the x-axis and different things on the y-axis and look at the distribution. And if I want to get all the different combinations, I want to explore this data set, I can do a scatter matrix, and it's in pandas. In pandas plotting, there's a function that's called scatter matrix. And I just put the iris data frame in there. And what it gives me is, so all the different combinations of sepal length against sepal length, here it only gives me a histogram, a histogram, and here's sepal width against sepal length, and petal length against sepal length, and petal width against sepal length, and it already shows me a bit the structure of the data. Another kind of plot that is sometimes useful is a parallel coordinates plot. It's also in PD plotting. So it's parallel coordinates. And I put the iris data in, and I want to sort it by name. And here it gives me different colors for the different flowers that I have. And then it just puts the different dimensions or coordinates that I have parallel to each other. So sepal length is here, sepal width is here, petal length is here, and petal width is here, and then they are just connected with lines. So these are just some basic plotting techniques that you can use to get a first impression of a data set. Before you start doing any fancy data analysis like deep learning or so, I would always do some simple plotting and see what the data looks like, right? So that you get some intuition about the data. Okay, I think that was the first impression of pandas. Any questions so far about pandas? Okay. So now we go a bit more into detail. One core difficulty in pandas is if you have a data frame such as this, then there's two ways that you want to address the cells of this data frame. One is by index, so you just say the column index, the row index and the column index, and the other one is it's by location. So you just say the third row and the third column. And the other one is by these names, by these labels. You select a label here and you select a label here. And so you have two fundamentally different ways of accessing data in a pandas data frame. And in the history of pandas, I think this led to a lot of confusion. So there are some old ways of indexing into data frames which were called .ix. Don't use this, it's deprecated. And recently, they cleaned up this mess a little bit, and they introduced one fundamental way for indexing by location, and one different fundamental way by indexing by label. So I recommend you always to keep it separate so that it's clear what you mean. It's getting especially confusing if the index here is also numbers, right? So if the index here is just integers, then sometimes it's not clear whether you're referring to the label or you're referring to the row number. So that's why I recommend you to always keep that clean. So let's start by label-based indexing. Label-based indexing. And the method is .loc. Loc for location. So let's look at our iris data set again, iris.head. So our iris data set looks like this. And now if we want to select some fields here by a label, we can say iris.loc. Then we have to give the label of the row. Maybe we want to have a row with label 3. And then the label of the column, petal length maybe. So this should hopefully be 1.5. And then you can also slice by labels, iris loc. And now there's something where you really have to be careful. Labels from 1 to 3, sepal width. Now here, this is the point I think where you have to be most careful in pandas. If you select by labels, the labels could be anything, right? The labels are not necessarily numbers. In NumPy, if you select by the index, And also in Python, if you slice a list, the last element is always excluded, right? If you do a NumPy, you say A from 3 to 15, then the 3 is always included, and the 15 is always excluded. Now if we have pandas, we have some series. 3, maybe the index can be letters, A to F. Here it doesn't make any sense to exclude the F, right? Because you're accessing by labels, s.log. So this one is included, and this one is also included. Or if you have some data frame or some series, and even if it looks exactly like this, 3 to 15, then this is included and this is included. So slicing works slightly differently. But only if you access by label, right? And it actually makes sense because with labels, you don't have this clear structure as with integers. So it doesn't make sense to exclude the last label. So Iris, if you go by labels, you start with the first label, or the label 1, you end with the label 3, and you take the column label sepal width, then you get this 3, 3.2, 3.1, and you also see here that the index, the row index is preserved. You always maintain the row index. And otherwise, I think it's very similar to NumPy. So you can iris.log, and you can say that you want the rows with the labels 77 to 80, and all columns, you just say this. Or maybe you just want a few columns. You say iris.log 80 to 82, and you want the columns. You give if you want to get a subset, you can give them as a list, petal length and sepal length. This slices some part out of your data frame. You can also slice like this, iris log from 80 to 82, and you want the columns from sepal width to petal width. Here you can also just slice some range out of your labels. You can also say iris log all rows, just the column name, and you want the head of this. Looks like this. Gives you a series with the names. And now what you can do, if you say iris.log all rows, column name, and you check where this is equal to iris setosa. This actually gives you a binary series where every entry is the result of whether the name is equal to Iris setosa, right? So maybe I'll just do the head of this to make it a bit shorter. So this gives you a binary series. And now what you can do is you can use this binary series to select from your data frame just the rows where the name is Iris setosa. And you just say Iris block. Okay, you want the locations, you want to make a selection of rows. And you want to have exactly the rows where the name is Iris setosa. So you want to have the rows where this thing here is true. You want to have the rows where this is true, and you want to have all the columns. And this is something that you actually, or I use all the time. So when I write something in pandas, I always want to slice something based on some conditions out of some data frame. And it's a bit, so for whom is this easy to understand what it does? Okay, maybe I can repeat it. So you take the Iris data set, the data frame, you choose all the rows, here, and just the name, and then you check whether this name is equal to this string, Iris setosa. And this gives you a long list, a long series, where it's true, true, false, false, true, true, and so on, depending on whether the name is Iris setosa or not. Then, for all the rows where this gives true, you select all the rows from the Iris data frame and all the columns. All the columns you select with this. And I think you probably have to practice this a little bit, but it's actually worth it because this is something that you use very, very often. Any questions about label-based indexing or selection? Okay, then the other way to select stuff from your data frame is by location. Selecting based on location with .ilog. And this works exactly the same as in NumPy. So I just say iris.ilog. I want to have row 3 and column 2, and this is exactly the same thing as in NumPy. So it's actually, if you already know NumPy, this is easier, I guess. Iris.ilog, you want to have row 3 and columns, all columns. This is what you get. Or you say that you want to have row 3. This is the same. So you just saying you want to have row 3, or you want to have row 3 and all the columns. It's just as in NumPy. I can say iris.ilog rows 2 to 5, and then columns, you give them as a list. Columns, first column 3, then column 1. This is first column 3 and then column 1. Or iris.ilog rows 3 to 8, columns 0 to 4. This is actually interesting because now you have sliced the part out of out of the data frame which contains only numbers, right? So maybe we can try to convert this part here into a NumPy ND array and see whether it gives us nice numbers. So we select this part and then we get the values. We put them into some matrix B. Now the type of B is ND array and B is this. B type. Now you actually, Pandas gave us an ND array with data type float, right? So now we can actually do some arithmetic. So pandas tries to be smart. If there are strings in your data, it cannot give you float, right? It has to give you object. But if everything looks like a float, it gives you float as a data type. You can also mix. Log label-based indexing and location-based indexing. But I recommend you always to keep it a bit separate. So if you want to do some label-based indexing and some location-based indexing, for example, you can do iris.log. So you want all rows, and by label, you want the column with sepal length. So this gives you a data frame, and then from this you want to do some location-based indexing with ilog. And maybe you want to have row 164 to the end. Oops, that didn't work. Oh, length. There are some ways in pandas where you can mix like location-based indexing and label-based indexing. But I find it a bit confusing, so I prefer to keep it a bit separate. Okay, so in pandas, there's this different ways with log and ilog, so either based on the label or based on the location. And then there's something called convenience indexing, which lets you do both at the same time, which I think most of the time it's super confusing. But I show it to you anyways. But you have to be very careful with this because I had a lot of bugs in my code with this. So there's strange things happening. So there's convenience indexing. And this is just iris. We already saw that. You just put the brackets as in NumPy. And this, I think I'm not exactly sure, but I think what this does is that pandas tries to guess whether you mean the label or the location. And maybe pandas is right, maybe pandas is wrong when it guesses. So you have to be a bit careful with this. I think if you want to select entire columns, it's okay. Iris, select the column name, and then check where this is equal to iris setosa. And maybe only want the head of this. So this works. And pandas tries to guess that with this you mean the label. This allows you to do the stuff that we did up here, this one, a bit shorter. So we can say iris at the location where iris name equals iris setosa. It's very short. It works most of the time. But when I coded this, sometimes I had some strange problems. Okay, now let's go back to the scatter plot that we did up there. So up here, I did this scatter plot. Where's my scatter plot? Here's my scatter plot. And here the problem was that I couldn't distinguish which one was which flower, right? So let's try to do 3 different scatter plots in one, just to color them differently. So yeah. Maybe we can create 3 different variables. Setosas. Let's first do all the setosas. And this is iris at the position where iris name equals iris setosa. Then we do where the colors as iris at the location where iris name equals iris as a color. And then Virginicas is iris at the position where iris name equals, iris Virginica. Okay. Let's look at setosas. Setosas head. Oh, that looks okay. Here's the colors head. Oh, that's okay. Virginica's head. Okay, I think that looks fine. Then let's say that my diagram is, first I plot all the setosas. Plot scatter. And on the x-axis, I want the sepal length. And on the y-axis, I want sepal width. Okay, how that works. Okay, now let's try to plot the 2 others into the same diagram. So I also want to plot the versicolors. Versicolors. And now I have to say that I want to plot it into the same diagram. And I hope this is axis. I have to say axis equals diagram. Let's hope that this works. And then I want to also plot the Virginicas. Also into the same diagram. Axis equals diagram. That didn't work. Unknown property axis. Maybe it's X. Let's try this. Okay. Now they're all in the same diagram, but they are all the same color. Let's hope that we can say. Does this work? Blue, that was not very smart. Wait. Color equals pink. Okay. Now we can see that these setosas, they are up here. The versicolors, they are down here. And the Virginicas are up there, but the versicolors and the Virginicas, they are a bit mixed. Right? Okay, let's do a little bit more practice with selections. Say we want to have, we want to select all the flowers that have a small sepal. So we do a new data frame that's called small sepal. And this is equal to iris at the location where iris sepal width is smaller than 3.0. Small sepal head. Okay. Now here all the sepal width are smaller than 0. And let's plot these. Small sepal plot style equals maybe pluses. And now we plotted all the flowers that have small sepal. So we skipped the ones which have bigger sepals, and these are the ones that have a small sepal. Okay. Any questions so far? Yes?
Why are the pink nodes in the scatter? Some are bigger than others?
Again?
Can you roll it up?
Here?
The pink,
The pink ones?
something bigger than smaller. Why is it not the same?
I think the bigger ones, they have a red one behind them. Maybe. Maybe there's two flowers which have exactly the same, but I don't know. I don't know what the reason is. But I could imagine that there are some flowers which have exactly the same sepal length and sepal width. Maybe. But maybe not. I don't know. I don't know what the reason is. I think it depends on the plotting order. You can select a different style, maybe. Style equals, maybe let's do pluses. Like this. Oh, that didn't work. Oh, no, I don't know what the reason is. Sorry. Okay, then what you quite often want to do is you want to write into some arrays. So you want to do assignments. So if we look at our iris dataset, it looks like this. And maybe we want to add a new column that contains only ones. And for this, we can say iris log. We just ask for a column that doesn't exist. We take all rows and a new column that doesn't exist. Let's call it 1. And we set that equal to 1. And now we added this new column to the data frame and filled it with these values. Maybe we want to fill it with the numbers from 1 to how many columns we have. So first we need to know how many rows we have. We can say iris.shape. This gives us the rows and columns. And iris shape 0 gives us the number of rows. And now we can add a new column, iris log all rows, column, let's call it count. Let's fill that with a range of iris shape 0. So here we just count from 0 to 149. We do a range of that, and we fill that into count. And now iris looks, now iris looks like this. You can also write into individual fields into the data frame. So you can say iris log row 1, row with label 1, column with label count. We set that to 12. So now we set this field here to 12. And you can also fill multiple of them. So you can say iris at the location row labels from 1 to 3. Now 3 is inclusive. Column label count. Let's fill that to 22. And now we wrote 22 into these fields here. You can drop entire columns with the del keyword. So you can say del iris count. And now hopefully iris head. Now hopefully this column just got deleted. You can also add some new columns based on some calculations based on the other columns. This is what you actually will do quite often. For example, you can add a new column that says whether the petal is particularly long. So you can add a new column. Let's call it long petal, which will contain true and false values. And this should be iris at the location petal length bigger 5. Oh, is that df? It's iris. Sorry. And now we added this new column here, which is actually a calculation based on the petal length column. Or you can add another column, a petal ratio. So you can say iris. You can also do it with the log command. So this is convenience indexing. This is label-based indexing. So all rows, column, new column, which we call petal ratio. Which will be iris, the column petal length divided by iris column petal width. Oops, that didn't work. So it complains, oh, petal width. So, okay. So all of this is stuff. What's nice here is you can write in 1 or 2 lines of Python some stuff that will take you like 2 pages of C code, if you prefer to write C code or Java code. And it will also run much faster in many cases, unless you're a C wizard. But most of the time, here you can write really a very few lines of code. You can do a lot of data manipulation, a lot of cleaning of your data. It will run very fast, and it will also, it's much easier to find bugs here, I think. If you have like a 2-page C code that does all these data cleaning for you, it's very difficult to find bugs in there. I have another box plot example. So let's do a new data frame that is iris. So let's pick 2 columns. Let's pick the column name and the column petal ratio. So this is for just a petal ratio. And if you do it like this, then what pandas will do is it will reorder the column. So now name will be the first column and petal ratio will be the second column. So now the first column here is name, the second column is petal ratio, and the row labels are still maintained. And now we can do PR box plot by name, and we get a box plot of the petal ratios. And there's also a replace function. So let's do an iris2 data set. So we take the iris data set and we replace all we replace all occurrences of the string iris setosa. Maybe it's too long for us, and maybe we want to shorten it with S, I think. That would be sufficient. And now here the name. So all the occurrences of the string iris setosa got replaced by the letter S. So sometimes, I think for the rest of the entire lecture or the entire course, when we work with data, we will load the data with pandas, then we will shuffle the data a little bit into something so that we can generate an ND array out of that, and then we will continue to calculate using the ND array. And one thing that will be convenient is if we can change the order of rows, if we can change the order of columns. So if we want to have only the values, for example, we want to get rid of all of this and we want to get only these values here. We get a new data frame. We take the iris data frame, add the labels. So most of the time we want all the rows and we want the columns in a specific order. So maybe we first want sepal width. Then we want petal width. Then we want sepal length. And then we want petal length. Okay, now it looks like this. And then we want to maybe put that into a matrix. So we will say A equals iris values. And then we have this ND array where we can do calculations with it. Maybe. Okay. Now I think we proceed into some more advanced stuff. So I think these are all the basics that should already help you to do a lot of calculations with some data that you have. Now there's a few nice details. Oh, but actually we don't have much time left. Maybe I can show you one. So one nice detail is that the index is always being preserved. So if you have, let's say you have a time series 1, S1, so you can create a new time series like this. From maybe you have 1.1, 2.1, negative 3.1, and 1.3. So you just give it a list, and you give it an index. You say that the index should be also a list, B, C, E, and F. Now your time series looks like this. And now you can add something. You can say S1 plus 3. And it just adds 3 to each of the values, but the index is being preserved. Or you can say S1 divided by 2. And it divides all the values by 2, and the index is being preserved. We already saw that you can select a subset. For example, you can say S1 at the positions where S1 is bigger 0. Gives you only the values that are bigger than 0. And then say you have a second series, S2, as PD series 2.3.2, 2.7, negative 1.1, and 1.2. And you have a second index which is A, B, D, and F. Now you can see that S1 is this, and S2 is this, and both of them have different rows. So if you do S1 plus S2, it gives you at all the row labels that were in S1 and S2. It gives you the sum of them, and where it cannot compute the sum, it gives you not a number. If you want, instead of not a number, if you want to have zeros in the case where one of them is not available, you can say S1 add S2 fill value is 0. And by this you can add two time series which are which have different rows, which are differently indexed. Okay, I think this can already help you in a lot of your projects and maybe bachelor or master thesis or PhD thesis or work afterwards. And I think we have a few more things to say about pandas next week and a few more advanced NumPy style things next week. So have fun with the exercise sheets and see you next week. Thank you.